So now we want to go back to the molecule in the box and mark all of the chirality centers, all of the carbon atoms that have 4 different things attached to them. And so the first thing that we're going to do is rule out carbons that have 2 or 3 hydrogens, because if you have 2 or 3 of the same thing, you cannot be a chirality center. This first carbon has 3 hydrogens, so it cannot be chiral. This one has 2 hydrogens, so it cannot be chiral. This one can't. This one can't. No, 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 and no. So our only options are this carbon right here and this carbon right here. Those are the only ones that only have 1 hydrogen on them. That doesn't mean that they're chiral, it just means that we need to look at them more closely. So we'll start at with the one on the left. The one on the left has a hydrogen. It has a methyl. I'm going to erase this circle. It has this 3 carbon thing, and then it has all of this, whatever that is. So those are 4 totally different things, which means that this carbon right here, yes, is chiral. Now let's look at our other one. That carbon has a hydrogen. It has a 2 carbon branch, a 1 carbon branch, and then all the rest of this molecule out here. Those are 4 different things. So it also is chiral. So both of those carbons are chiral. Number 9, could this reaction be used to synthesize the molecule in the box? This is hydrogenation. Remember, in a hydrogenation reaction, we are simply switching from a double bond to a single bond. That's the only thing that's happening. So if we do hydrogenation on this molecule right here, here is what we end up with. Does this match the molecule in the box? Yes, it does. So yes, this would work. What is the relationship between the molecule in problem 9? That is not referring to the product. The molecule in problem 9 and the molecule in the box. How are they related to each other? So this is similar to question number 7. The first thing that we should do is find the molecular formulas. We know the molecule in the box is C10H22. What's the molecular formula for the guy in number 9? It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So that matches so far. How many hydrogens does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Don't let those double bonds fool you. This carbon right here has 1, 2, 3, 4 bonds. Double bond counts as 2. So C10H20, they have different molecular formulas, and if you have different molecular formulas, you do not have any relationship at all. All right, for question number 11, looks like 11, 12, 13, and 14 are all based off of this molecule here in the center. First thing we have to do is classify it as cis or trans or neither. So to classify it, remember we want to draw an imaginary line through our double bond. We want to look for something on this side of the double bond that matches up with something on this side. Now it looks like we have this 1 carbon branch that's present on both sides of the double bond. So that makes this a trans molecule. Now we need to draw the product of reaction with bromine. And I'm going to do that one first, even though it's number 13. So when we're drawing the product of the reaction with bromine, Br2, we're going to draw the molecule exactly the same way. I'm not changing anything about the carbons, but we've switched the double bond to a single bond. And then we are going to attach 1 bromine to each carbon of the double bond. So there's our product for reaction problem 13. For problem 12, very similar. We're going to draw the carbon chain. We're changing the double bond to a single bond. Find your business carbons. We're going to put a hydrogen on one carbon and a chlorine on the other. Where does the hydrogen go? The hydrogen goes to the carbon that already has the most hydrogens present. How many hydrogens are on this carbon? There are 0. How many hydrogens are on this carbon? 1. That means it's going to get the new hydrogen. The other carbon is going to get the chlorine. So there's that product. And then what is the name of that molecule? I'm going to erase so we can see it better. When we're naming, we want to find the longest carbon chain. So that means we're going to start at any end and go to any end, but we have to go through the double bond. So one option is to go like this, and that would be a 4 carbon chain. Another option would be to go like this. 1, 2, 3, 4, 5. That would be a 5 carbon chain. So that's the option we want to take. This molecule's longest chain is right here. Now we need to number it, starting at the end closest to the double bond. So that's going to be starting on the right side. Locate the position of our substituent. Our substituent's on carbon number 3, and the substituent's name is methyl. So we know we have a 3-methyl, which means we can get rid of option A and option D. 3-methyl, now we locate the position of the double bond. And this is tricky. When you're locating the position of the double bond, even though it goes across 2 carbons, this one goes from 2 to 3, you only say the location of the first carbon. We only say, in this case, we only say 2. We don't say 2, 3, we just say 2. 5 carbon chain, pent-ene. So your correct name is B. And the last one on this page, we're supposed to draw the enantiomer of this molecule. When we are drawing an enantiomer, the easiest way to draw an enantiomer of a Fischer projection is to just draw everything backwards. Just drawing a total mirror image. CH2OH.